Okay, so this is something we still have yet to address when it comes to our little bits of fluid. We have to describe the forces happening on them. But I hope now you understand we've at least tackled this part of the idea of prescribing motions with an equation. That's what Newton's laws does, is you tell me some forces, and I'll tell you how that particle moves based on this equation. So ours is different because we now have a different way to describe this. This is now, right, this material derivative like this. And then for mass, we haven't talked about that yet either. We have to extend these definitions. But, right, I mean, mass of any sort of volume of fluid, right? This is where density is so prevalent in all of fluids because, right, here is some sort of volume while the mass is the density of the liquid times the volume. That's just what we define density as. But now you can see that this rho part itself can be a function of all these variables just like this. So V, right, before when we were trying to describe the A, we had a vector field. So for every point in space and a given time, I'll give you a vector. This density now, one complicated thing is it could change throughout a region in space as well. If I have some arbitrary thing of fluid sitting in a coordinate system, right? This could have a density, this could have a density, and there's another one that could have its own density, like 1, 2, 3. So this is where conservation of mass becomes critical for all of our fluids equations. I mean, F equals ma is a conservation of momentum. All physics equations are just conservation equations. So conservation of mass allows us to describe how this density can change. And that's important for compressible fluids. And for incompressible fluids, that's where giant simplification will come from. So in the book, there's a control volume approach to this to show you what the continuity equation of fluids are. And it uses these things called control volumes, which I'll go over later, but kind of a quick one I just kind of like to do is if I want to conserve mass in some system, right? And this thing moving in a coordinate system, right? It's moving around, and I can draw any sort of small ball around here. These are control volumes, right? And I'll call that, like, let's say, volume control volume. So conservation of mass is saying for this, if I consider only all of the mass inside of this region, and I even let it like undulate maybe around time, so it would change its surface itself, well, the mass has to be conserved. So then, right, then I kind of just do this, something like that. And then this, we'll say it, right, and then if it's small enough, right, you just say that this is a constant value. Something like that. So then conservation of mass looks like that this term has to be 0. Okay, so we expand those terms out because we have, right, a definition of this material derivative, and you'll get, and then we'll have one little dot. This is what we said it was, and then it'll be something like this. So this all has to be equal to 0 if I'm going to conserve the mass of some all the small little regions or small bits of fluid in a volume of liquid. Well, this is exactly where the idea of incompressible liquid will come into play, because if I say that the field at every single point in this blob of fluid, I'm going to just call that some constant. Let's call it rho naught, right? Now, if I do this, this term goes away because this is a constant. Derivative of any constant, 0. And then what you're left with is this term right here. There's something that won't come out if you just straight up apply the material derivative, but like really one little trick you can just do is you have this. You just flip these. So again, if it was compressible, this goes away, and I still have this equal to 0, and then you get the continuity equation, which is used all over fluids, and that's just that since this is a constant, pop back out. Right? Right? This is a constant value, so it's non-zero. That means that for conservation of mass, you get this divergence-free velocity field. And this equation is used a lot to predict velocities given one of them. And we can see that later on when we use it later. But right, haven't gotten to the summation of forces yet because I want to save that for the harder part. But we at least now have a way to describe fluids just as simply as, we'll do this, we're doing a mass so this is also why in fluids everything's on a per unit volume because that's dividing out by this. So divide out by unit volume. Lowercase letters usually represent per unit volume, and you get this. Just appreciate that we have an understanding of what this term means now. If it's constant, this isn't that bad. So it's not, we haven't gotten the compressive effects yet. And this is really the hardest part about fluids is describing these forces, because you have to describe the forces happening on the center of mass of a little bit of fluid and on the outside of the fluid. But we also now have another conservation equation, which is continuity, which for an incompressible liquid is that. So this is a very important equation. Write that one down.